Ashwinji. So, Hari Om everyone. So,
yes, has the live streaming started?
Yeah.
Yeah.
So, welcome again to Ascent Talk. In this month's talk, Pranav, who is from Princeton University, will speak on multiple realities and its implications in both
Yes, Ravanji, you
science
can
and
start.
Vedanta. Okay. So, welcome Pranav, and over to you.
Okay.
So, welcome Pranav. Which reality are you speaking from?
One of the realities.
One of the realities.
Yeah.
Are we in the same reality or are we in the different reality?
That I don't know. That is you should conclude after the end of this talk.
Okay.
I will
Okay.
just give you the principle from you can draw the conclusions.
Okay. Okay.
Oh, I can't screen share. It says host as disabled.
Okay. Ashwini ji, can you enable Pranav for screen share?
Oh, yes, Pranav ji, you can share.
Yeah.
Okay. So I'll start.
Yes, Pranav ji, continue.
Yeah. Hi everyone. So welcome to another talk in Ascend, and today I'll be talking about multiple realities. So in this talk, what I'll mostly do is I'll give you a few interpretations. So these are not established theories. These are what we call as interpretations in science. So when you have some concept in physics, you can have theory backing that concept, which is actual physics on how things work. But there can also, beyond that, there can be some interpretations of what it could mean, which aren't really tested yet, but we strongly believe that it could be one of the ways that things are happening in the universe. So, uh, so I'll be talking about these interpretations today, and I find that these interpretations that we have, particularly these interpretations, uh, are very close to some philosophies that we have in Vedanta. So, this is what I will discuss today. Oh. Okay. So parallel realities, parallel worlds. I'm going to just keep interchanging these two realities and worlds. You guys can decide what is what later on, but I'll continue with with these terminologies itself. So, so like when we go through some trouble or something like that, like we always think, right? What if something like this didn't happen? Uh, what if I was like something else, instead? So I'm a physicist today, what if I was a software engineer? What if I was a teacher? I wouldn't have this kind of a fate or something like that, right? So we keep thinking about this parallel world that we want to dream about, that we want to live in. And people have been fascinated by this concept of having an alternate reality throughout. If you look at movies, there are these movies in English which has toyed around with this idea uh, of parallel worlds, multiple universes, and more recently, if you go through these comics, if you go through DC comics, like there are these multiple parallel universes. It's called as the multiverse. And then also, if you are more familiar and if you like Marvel more, there's a concept of this multiple universe over there as well. It's so essentially people are fascinated by these realities that exist in an alternate universe where things are happening right now might not happen in the same way. And it's the person and the interactions are all the the person, the interactions are the same. It's just the outcome might be different. For example, right now I am talking to you. uh, in some other universe, I might not talk to you at all. So it's kind of like toying around with that idea. So, uh, is there some way where we can understand multiple real? So this is all nice science fiction and stuff. But is there an analogy that we can draw in science itself, in the present understanding of physics that we have? Is there some kind of a concept of multiple realities? Is what I'll be discussing now, and it turns out there is, and it always goes back to one of these things, quantum mechanics. In a wonderful theory, a wonderful thing in physics where things are always counterintuitive and allows for a lot of different things. And apparently, you can have a nice interpretation of multiple realities if you look at how quantum mechanics works. So this is what I'll be talking about in today's talk, and I'll be drawing analogies based on this interpretation. So to mm, first, let's take a simple example uh, on how weird quantum mechanics is. So so over here, there's an experimental setup. It's a simple experiment. So I have a gun. I'm going to fire a bullet, and when I fire the bullet, I can either shoot the bullet through a slit. So it's like a narrow open, it's an opening essentially. So I can shoot the bullet through the opening on the left, or I can shoot the bullet through the opening on the right. So based on that, once I shoot the bullet, it's going to pass through this opening, let's say, and then it's going to hit an observing screen. Okay. So if you shoot the bullet through the left hole, then it's going to fall on the left on the screen. Similarly, if I shoot the bullet through the right hole, then it's going to fall on the right side of the screen, right? It's simple. So if it went through the left, it's going to hit on the left side. If it went through the right, it's going to hit on the right side. Now, I'm going to repeat the same experiment, but instead of a gun and a bullet, I'm going to shoot one electron instead. So electron right now is going to be a quantum particle. So quantum mechanics is the rules that apply to an electron. And when you have quantum mechanics, this crazy thing is what you see on the screen. So if you shoot one electron, it turns out the electron passes through both holes. So it's like the electron is going through this hole also, the left hole also, and the electron is going through the right hole also. And this is what you see on the screen. It seems like the electron is going through both holes, which is very, very weird, right? How can how can one single electron be on the left side and the right side at the same time? But that is what is happening. And that is why quantum mechanics is extremely weird, something that even we don't understand properly yet. So, like I was saying, this single electron unlike the bullet, where you can definitely say that it went through the left hole or it went through the right hole, the single electron seems to go through both holes at the same time. Okay, so that was a proof of that was like an explanation of the concept. Now we can take this concept to a higher to a higher level, and we can think of all sorts of thought experiments. So this Schrodinger cat that I'm about to explain is a very nice thought experiment in quantum mechanics. So what it essentially says is, so the experimental setup is simple. So there is a box. The box is closed and there's a cat inside. So there's a cat inside a box. And then what else do you have inside? You have this bunch of stuff. I'll tell you what these are. So what you have here is one radioactive atom. So it's an atom. So atoms are essentially atoms are essentially these kind of building blocks that make up the universe. So for example, if you have salt at home, it's made up of two atoms, sodium and chlorine. If you look at our atmosphere, it's made up of the majority is made up of this atoms called nitrogen. We have oxygen there. Then if you look at carbon dioxide, there is carbon and oxygen as atoms, and so on. So this atom is unique. It's made up of it's a radioactive atom in the sense that it is an atom which is nuclear. So if you must have heard of this nuclear energy and stuff which you use for energy production and like for making weapons and things. So this is essentially a radioactive atom. So if you have heard of uranium, it's a radioactive atom. So you can think of just as one atom of uranium. So there's a radioactive atom here. There's a detector that detects what happens inside this radioactive atom. Now this detector is connected to a hammer, and the hammer is connected to a poison bottle. Okay. So what essentially, so the experiment is essentially this radioactive atom is a quantum mechanical particle. Okay, what it can do is it can suddenly give away another particle called a neutron, or it need not. Okay, so it's going to give a neutron, or it might not give a neutron. But this is a quantum mechanical. This is a quantum mechanical this is a quantum mechanical particle. So there is some weirdness to this thing that I just said, and I'll show you how it comes. So finally, the concept is that if this radioactive atom releases a neutron, let's say it gave away a neutron, what happens is this detector will detect it. This hammer will be activated. It will go break the poison. And the poison will be consumed by the cat, and the cat will die. So essentially, the whole process is like this, and this whole thing is this cat is essentially linked to this quantum mechanical particle. So if a neutron is fired, this one will detect, it will activate the hammer will break the poison bottle, and then the cat will die. But if it didn't release a neutron, then this one doesn't detect, the hammer doesn't get activated, the poison bottle is not broken, and the cat is alive. Okay, so if you just think of this experiment purely from just the cat's point of view, if you didn't have all these complicated mechanisms where the cat is not tied to the quantum particle, then the experiment is simple. So if you open the box and if you observe if the cat is alive or dead, there can only be two outcomes. One, that the cat is alive, then the statement cat is dead is wrong. So if the cat is alive, then the cat is not dead, right? Or if you find the cat to be dead, then the statement cat is alive is wrong. If the cat is dead, then the cat is not alive, right? So the cat can either be dead or be alive, right? If you open the box. Now, if you didn't open the box also, you know that the cat is either alive or dead. It can't be both. The cat can't be alive and dead at the same time, right? But in quantum mechanics, things are weird. Like I said, just like how the electron can go through both holes, this radioactive particle over here, it is in so the radioactive particle is actually both releasing a neutron and not releasing a neutron at the same time. Just like how it passed through both holes, which you can think of as two regions in space. Right now, the radioactive atom, which is uranium over here, let's say, turns out it is in a combination of these two realities where it has released a neutron and not released a neutron at the same time when the box is not open and when you're not looking at it. So it turns out because this is in a superposition of two realities. So there are both the realities are together. It has released a neutron and not released a neutron. Both of these are combined and both of these are together. And because this radioactive atom is tied all the way to the cat through this complicated mechanism, the cat is actually, when you're not looking at it, the cat is actually both alive and dead. So it's kind of like this. So you can't conclude anything. It's actually a combination of both realities. So the cat is both alive and dead. So which is extremely absurd, right? How can something be both alive and dead? But that is the way nature is, and we have to take it. And it turns out nature always prefers to be this kind of a quantum mechanical thing. So it's always both alive and dead at the same time. So this is this famous thought experiment, and Schrodinger is the one who came up with this. So it's called as the Schrodinger cat. If you guys want to know more about this, you can always just Google about Schrodinger cat. It's there everywhere. And this is the beauty. This is one of the really good beauties of quantum mechanics. It's cat is alive and dead at the same time before you actually go ahead and measure and open the box and actually see if the cat is alive or dead. Okay, so next I'll go to the interpretation of it. So what does it actually mean to have, when I say cat is alive and dead at the same time, what does it actually mean? So there are quite a few interpretations in quantum mechanics because when this came, it totally blew the scientists out of their mind, and then everybody tried to come up with a lot of interpretations. Finally, I would say there are three main interpretations in quantum mechanics that are kind of like distributed among scientists. But the most famous interpretation is this Copenhagen interpretation. So I'll be talking about this, and I'll be talking about the next famous interpretation, which is the many worlds interpretation. So I'll be talking about this first, and then I'll talk about the many worlds, and then I will bring both of them together, and I will show how parallels can be drawn in these interpretations and Vedanta. So the first interpretation, which is called as the Copenhagen interpretation. So I'll just briefly go through this. So what do we have here? So we have before when the box is sealed, if the cat, like when there's a cat inside a box and the box is not open, you for sure know that, the cat must be either dead or alive, right? It can't be both. But now you have this weird cat which is tied to a quantum mechanical experiment. And now quantum mechanics says you can have both dead and alive. And so essentially, because the cat is tied to this tiny uranium particle, the cat right now, if you don't open the box, is both dead and alive, right? And quantum mechanics also says the way you can only confirm things is only when you observe it. So how do you know if the cat is dead or alive? The only way to do it is actually go ahead and measure it, which is to open the box. So if you open the box, the cat is either found to be dead or alive. It's not going to be dead and alive at the same time. So Copenhagen interpretation rests completely on this so-called thing as called as measurement, which is the action of actually probing the system and seeing whether the cat is dead or alive. So initially, what you have is there's something weird where cat is both dead and alive at the same time. Then you come in and you make a measurement, you open it. So you're curious now, you want to know if the cat is dead or alive. So you make a measurement on it, and then you find out that the cat is either dead or alive. So first what you had is this weird combination of dead and alive. The only time you know the cat is dead or alive is only if you make a measurement. Only if you go and observe do you know that the cat is dead or alive. Before making a measurement, before making an observation, the cat is both dead and alive. So in this interpretation, people often run into this problem called as the measurement problem. So this problem is still unsolved in physics. We still don't know how measurement happens in quantum mechanics. So this is a measurement problem. So, based on this, you can ask a lot of fun questions. So I mentioned two of them here. So, based on this, so until you measure, you don't know if the cat is dead or alive, right? The cat is both dead and alive. So you can extend this to a lot of things. So one famous question is, does the moon exist when I don't observe it? So when you observe it, you see the moon and you say the moon is there. Or if it's the daytime and you look at the sky, you say the moon is not there. You don't see the moon and you say the moon is not there. But when you are not observing the moon, when you don't look at the moon, how sure are you that the moon is there or not? Because the moon could be doing something crazy, like the moon is there and not there at the same time, right? So does the moon exist at all when I don't observe it? Is one of the fun questions that pops up like this. And the other question is, since everything is dependent on an observer and the final observer, so you have a bunch of complicated instruments through which you probe, but the final observer is actually you. So if everything in the universe were to be quantum mechanical, then is the world just a measurement dependent on only the observer, the final observer, which is me? So is everything that is jutting out in the world, is it just a projection that solely relies on what I am, or is it something else? So you can have these kind of fun questions, fun philosophical questions based on interpretations of this kind of a particular interpretation of quantum mechanics, which is Copenhagen interpretation. The other fun thing is something called as multiple realities. So this is called as the mini world interpretation. So the reason why this interpretation mainly came up is because scientists had this problem of measurement. So it's 100-year-old problem. As soon as quantum mechanics came up, people realized that measurement is a problem, and scientists today, even now, we still don't understand it. It's still a problem in our heads. So this interpretation, the many worlds interpretation, came up to avoid this measurement problem. So what this one says is there is no observation at all being made. So the problem of a measurement comes only if you think that the world outside is different, you are different, and you are making a measurement, and that's how the observer sets in. The many world interpretation says, well, there is no observer at all. Everything is just a quantum mechanical superposition, and everything is just happening, and everything are just and everything is just happening, and our universe is just one of the realities. And there are these multiple realities that go on and exist that we don't know about. Our reality although it seems to be special, is not really special. It's just one of the realities that is just going on and on and on. So if you look at this quantum mechanics, so if you look at this, so it's like, no, the cat is dead. So let's say this is, you're going a long time. So this is cat is dead, cat is alive. Then from here again, cat is dead, cat is alive, cat is dead, cat is alive. And so, you can choose one particular timeline. Let's say cat is not dead, cat is alive. And then this is the reality that we live in. But then you could choose some other reality as well. Cat is dead, or cat is alive, cat is alive, cat is alive, cat is dead, and so on. So, so what the many worlds interpretation says is essentially now there is no differentiation between an observer and what is observed in the universe, because everything is just evolving along with the universe itself. The entire thing is just evolving. And whatever reality we missed out on is not essentially something we missed out on. It's just another reality that is there in the universe that we don't know. And there's nothing special about this reality. It's just that all these outcomes are just there. Just like how you have multiple worlds, you have all of these multiple realities that come up. And so there's no chance that you choose dead over alive. The cat is dead over cat is alive. Cat is dead is also there, cat is alive is also there. If you open the box and you see that the cat is alive, there is another world, equivalent world, where cat is also dead, and that world is going on through its own reality, and this world is just going on through its own reality, and both realities are the same, but it's just that we can't know each other. That's it. So like I said, so let's say you open the box and you said the cat is dead. So is there anything special about that reality? Well, not yet. I mean, it's not true. All realities are equal and the same. There's nothing special about this universe. Essentially, if you find the cat to be dead, there's an equal reality that is happening, an alternate reality where the cat is alive also. So there's no differentiation. This reality that we have is just one among infinite realities that are happening. So, and everything, since all realities are weighted equally, everything is happening and everything is predetermined, and then there is no space for chance at all. So this is the second interpretation, which is the many worlds interpretation. So finally, my favorite part, where I try to compare and draw some parallels between physics and Vedanta. So if you look at these two interpretations, these philosophical questions that I just posed also form very core concepts in Vedanta as well. So let's look at both of these together. First, I'll discuss the science, and then I'll discuss the Vedanta part, and then we can open up for questions and debates and discussions. So, if you look at the Copenhagen interpretation, the first interpretation where I said everything is dependent on the observer, on the measurement. There's only one universe, and what happens to the cat eventually is dependent on the observer. As soon as he observes, the realities collapse into just one particular reality. So this is what the Copenhagen interpretation talks about. And it says there's a quantum mechanical collapse. So all the realities collapse into the reality that we now know. And this is triggered by the observer. As soon as you observe, the realities collapse. So, and for this, an observer is required, and everything is just dependent only on this observer. Whereas in the many worlds interpretation, this collapse is not there. All realities exist. This is just one particular reality that is there. And this is evolving in a very determined, all the realities are just equally weighted and all of them are just moving in a predestined way. So if you look at Vedanta, we have similar concepts. So we have, so if you look at the first interpretation, we have a similar concept where the universe is essentially in the eyes of the beholder, right? So the universe exists because I exist. So it's a very nice parallel that you have. And, people, if a person is from the science background and if he's interested in the interpretations of quantum mechanics, then you can see that there's a very nice parallel between what the Copenhagen interpretation says and what Vedanta says, because essentially everything finally rests on this one particular observer. Has he observed it or not? Right? And then if you look at the many worlds interpretation also, there's a nice interpretation in Vedanta as well. So like I said, there are all of these parallel realities, and there is nothing special about any reality, right? So in Vedanta also we have that the universe evolves in a way which we can never know completely. So it's nothing can be known. All we know is there is this one particular. All we know is that there's a God, Ishvara, um, who 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 uh, who works this universe out, everything out in a very predetermined way. And so we know that everything is evolving in a predetermined way. There's nothing for chance. We say so we say everything is already decided. And so like everything is already predetermined, and the way this reality evolves or some other reality evolves is already predetermined, and everything is just happening. So if you look at these two interpretations, you have these nice interpretations in Vedanta as well. So this is what I feel that you can draw from these interpretations. Now let's see what you guys have. Thanks.
Thank you, Pranav. Can you stop screen sharing?
Yes.
Yeah. Thank you. Wonderful explanation about Copenhagen's interpretation and multiple universe interpretation.
Yes.
Ramana Maharshi speaks of Arunachala mountain. So he speaks of both things actually. One thing is that observed exists because of the observer, one way. Then he says in the Arunachala mountain, there are many siddhas and saints are there in a invisible form. So is he speaking of Copenhagen interpretation and multiple universe simultaneously? This is the third possibility.
Yeah, why not? I mean, these are just interpretations, so we don't know what is the reality.
Okay. The second thing is in Yoga Vashishta, there is a Yoga Vashishta speaks eloquently about multiple universes simultaneously existing. So the king enters into a mountain and he finds that there is another Brahmaji and another whole world is there.
Okay.
Right. So now the question is it possible to switch from one universe to other universe, or is it possible to change the reality?
In this interpretation, no. Because as soon as you say I change the reality, then an observer comes in. So that whole explanation is that whole many worlds explanation is to get rid of the observer. So there is nothing called as an observer. It's just there is this one reality and there's this one another reality, and this is just picked up one reality. That's it.
So Copenhagen interpretation, there is a place for the observer. In multiple
Yes.
universe theory, there's no observer at all.
Yes, that's because the Copenhagen interpretation relies on the fact that there's only this universe that is there. There are no other realities.
Yeah.
And so in order to show, in order to come up with that, you need to introduce this initially, before you make any measurement, quantum mechanics says both are possible, both are there. So
Yeah.
cat is alive is there, cat is dead is also there. But then we observe only one thing. So at some point, these realities must collapse, and that is what this measurement does. So the realities collapse, and there's just finally only one reality, and that is the Copenhagen interpretation.
Right.
So it is based on the fact that only this universe is.
So in Copenhagen interpretation, I opened the box and I found the cat
Yes.
dead.
Yes.
Is the cat dead because I observed, or cat dead because already it is dead?
Yeah, so that's what. So if the cat is dead because it was already dead, then that's not quantum mechanical.
Right.
Here right now the cat is tied to that tiny quantum mechanical particle, which is both giving a neutron and not giving a neutron at the same time. So because the cat is all the way tied quantum mechanically, so this is a thought experiment. In reality, it doesn't happen because cat is still what we call as a classical particle, like a human being. We can't be dead and alive at the same time. But if there was a way to tie a human being all the way to that quantum particle, then the human being can also be dead and alive at the same time. It's just that tying this all the way to that quantum particle is increasingly difficult. So, but that particle is both giving a neutron and not giving a neutron at the same time. So then you observe it, and then at that time, either it has given up a particle, a neutron, or not given up a particle. So there's only one reality there.
So what we are observing is cat is dead is the effect of me observing the particle.
Cat is dead. Yeah. So finally, yeah, it's some measurement that you have made on the quantum mechanical particle.
On the particle. Actually, I'm not observing the cat. Actually, I observed the particle. That's what caused the cat to die.
So yeah, so it's kind of like that. Yeah. So if both are tied quantum mechanically, then it doesn't make a difference if you observe the cat or if you observe the particle, because both of them are tied. You can say it's tied up. So it doesn't make a difference. So if you observe the cat, so here the reason is because the reason it's tied all the way to the cat is because then the act of observing can just be opening the box and you observing.
Okay, got it. So in Buddhism, there is a understanding called dependent arising. Okay, everything arises simultaneously. Dependence. Each is like the universe is like a Indra's jewel. There are a lot of jewels hanging. Each is reflecting light of each other. So in this universe, what we are seeing today, are we all entangled quantumly? Everybody is entangled to everybody else?
Well, only the caveat is again, are we quantum particles?
Are we not?
Right now, no, because
you have made an observation already.
No, it's not. It's not like that. That's why this measurement problem is a bit complicated. That's why we haven't solved it yet. So, I mean, every particle has some quantum nature. So human beings also have what is called as a quantum nature. But the quantum nature itself in time can go away. So if something is quantum, it's not quantum for unlimited amount of time. The quantumness goes away. So if it's an electron, the quantumness can stay for a very long time, and so you can do all of these experiments, and you can see nice results. of quantumness coming because of these, like for example, that weird thing where electron pass through both the left side and the right side, that can be observed. But for a human being, quantumness lasts for 10 to the minus 30 seconds.
That's all.
Yes. So it's an extremely small period of time. That's why you practically don't see any quantum nature. For example, I can't pass through this wall and go to the other side simultaneously. You don't see a Pranav both in the US and in India simultaneously.
Uh-huh.
So that quantumness lasts for an extremely short period. So it doesn't matter.
Don't we, when we dream, don't we travel to another universe?
I don't know how you connect dream to physics.
In dream, I'm in a totally different universe.
Yes, sure.
So is it not a parallel universe?
But I never traveled there physically with my body.
You traveled in a dream, no? In a dream, you had a
That
dream
is
body
fine.
also, no?
That is fine. Dream body is fine. In physical body, we are concerned with what happens with the physical body. Physical body has not gone anywhere.
And I have another question. We are
Yes.
speaking of parallel worlds. So
Yes.
actually, the way you see the world is in your brain and nervous system. You
Okay.
see the world not in the outside, but you see the world in your brain and nervous system.
Mm-hmm.
So that's why I would say in the whole Earth itself, there are 8 billion worlds.
Okay. Fine.
Does it fit in your parallel reality theory?
It's not this parallel reality theory. So we have some other statements like that. Like for example, we have this famous question: if I see red, is it actually blue?
Yeah,
So, so we have that based on what is happening in our brains.
correct.
This is not quite that, in the sense that what we assume. So in physics, what we assume is everything is not dependent on an observer. In the sense that things are happening. So that's why this measurement problem is still a problem for us, because
Okay.
we don't know, we haven't decoupled these two. So for example, for us, if I don't see the moon, does the moon exist, is not a question at all, because the moon is always going to be there.
That's assumption,
It's
not a reality.
yeah. Yeah, so in physics we are yeah, so that's why this observation problem is such a nuisance for us.
Okay.
It's challenging everything.
Okay. Thank you, Pranav.
So, yes.
Yes, Shravan, you want to ask something?
Pranav,
May I go ahead, Pranav?
yeah, go ahead.
Yes, please.
Okay. What I wanted to ask is, how is the quantum theory? How is it linked to? I mean, what you explained about the Schrodinger's cat, that concept. How is it linked to this important principle in quantum theory of a light particle? Being both a particle of a photon, being both a particle and a wave. Can you just tie up the two? Yeah. And
Yeah,
explain.
so it's not just light, which is both particle and wave.
Yeah.
Everything is a part. So in quantum mechanics, everything is a particle and wave. The reason why electron exists on both, can go through both those slits, is because of its wave nature. So if you look at a wave, like let's say you are observing a wave, you're standing on the beach and you're observing a wave, right? Can you tell me where exactly the wave is in space? So if I fire a bullet, I can tell you where exactly the bullet is going.
Exactly.
But if I see a wave, the wave is just spread throughout the water, right?
Right.
So it turns out, if you take a quantum mechanical particle, it can behave like a particle and like a wave. So it's true not only for just light, it's true for all quantum mechanical particles. So this electron can go through both precisely because it acts like a wave. So if you look at a wave if you're standing on the ocean, and if you look at the beach, if you're at the beach and you look at the wave is essentially everywhere. You can't say the wave is just here. So that's how all these particles are. And it turns out, so the problem, the magic with these things is as soon as you observe where the electron is. So let's say you shoot a tiny beam of light, and you say from where my beam of light came. Then suddenly it will choose. It will act like a particle, and it will say, no, I am not in both places. I am just in this place. But if you are not observing, then it's like a wave. If you observe, it's like a particle.
Yeah.
So that's how quantum mechanics is.
Yeah. Okay. The observation makes it. Okay. Yeah. Please go ahead. Yeah.
Yeah, so observation essentially collapses these multiple realities, and it will tell you this is where it is.
Right.
Yeah.
So, is this principle the precursor, the forerunner of Schrodinger's cat principle?
Sorry?
Is this principle of the truth, or whatever you may call it, of the photon or every other particle, every other electron or everything else being both a particle and a wave, the forerunner, did this result in the development of quantum mechanics, whereby the concept of, as explained by Schrodinger's cat, came about?
If you're looking at the history, it kind of got developed. So the wave particle duality was actually not observed. So it came up later. I mean, it was all happening around the same time itself. I'm not sure exactly what year and what followed what. But it was, I mean, it was a continuous development that we had. So somebody made an experiment, and then he tried to explain it, and then some more experiments came. But the final really a good experiment that for me at least, that I would say that really sealed the deal is essentially this this experiment that I was explaining. It's called so this electron going through two slits experiment. So this experiment is called as the Stern-Gerlach experiment. I think it was done in 1930s, I guess. So sometime around 1930s, this sealed the deal. But but there were a lot of theories and everything that was already coming up, and people already had their interpretations by then. So this experiment really confirmed that particle is both like it has wave-like nature and both particle-like nature.
Pranav, I have one more question, last question.
Yes.
Ramana Maharshi says everything is predetermined, including lifting up my hand, including all both of us talking now.
Yes.
Okay, and Stephen Hawking speaks of a deterministic universe. Are they speaking of both same thing or different thing?
For me, both are different, because when Stephen Hawking says when Stephen Hawking is using deterministic in the sense of what we physicists understand what deterministic is, it's essentially that you can put you can essentially, if you were to model a human being, you can put, or if you were to model a particle. So he's saying that the way the particle works can be written down precisely with equations. What we observe is not that, because quantum mechanics is a purely probabilistic theory. It's not deterministic at all. So the collapse that we see when it chooses one reality over the other is a truly probabilistic event. So that is what Stephen Hawking says. Maybe there might be some ways where both of these interpretations can be tied together, but I don't know. But I feel what Ramana Maharshi says is something more fundamental than that. Doesn't is not restricted to the way that we understand determinism right now in physics.
Are we just movie characters playing, which is already movie is prepared and we are just being projected on?
Yeah, so that is what Ramana Maharshi says.
Okay.
So that is not what Stephen Hawking says, because we because if that was the case, then you should be able to write up. You should be able to know how the movie was played.
Okay. So, is Ramana Maharshi version, what he says, everything is predominant, is
Yes.
another way of seeing multi universes? Because I can't change anything. Everything is there. Only one fixed path is taken.
Yes. So
Is
that's
it
why I
multiple?
said, yeah. So that's why. So in the multiple worlds theory, then everything is deterministic. Right now, in the Copenhagen interpretation, quantum mechanics is probabilistic. In the other interpretation, everything is deterministic. So there it works. In the many world interpretation, that whatever Ramana Maharshi says works.
Okay, thanks,
So
Ram.
yeah. It's just that we don't know what interpretation works, or I mean that's why these are just interpretations. So now in physics, if you say many worlds theory is the right theory, then you'll have to show me where the other reality is also. So
It's a good chance that multiple
sorry?
universe theory, there's a good chance that multiple universe can get multiple Nobel Prizes.
Yes. Yeah.
So, but the multiple universe theory, by its very definition, that when you are in one universe, you are not in the other universe, makes it impossible to simultaneously, prove that there is another universe. Because once you step into a universe and try to prove it about the other universe, then it isn't there. Because you are constricted to one universe.
Yeah.
Yes.
Yeah, the burden of proof is avoided.
Yeah.
It is there and you will never know.
Yeah, that's why these are interpretations now.
So, Pranav, one question that I have is consciousness.
Yes.
Some of the scientists now say that consciousness is reality. Now, assuming that consciousness is a reality in the sense that based on consciousness, one of these things is possible. An observer means consciousness. There is conscious observer. Now, if that's the case, can I say in the multi-world theory, there is no place for consciousness? There's no observer.
You can say there is some sort of a universal consciousness that is dictating how these universes are evolving.
But there is no consciousness across universe, across realities.
So again, in physics, we don't know what consciousness is. So if you are tying it to an observer or somebody who makes a measurement, then there is no measurement in the many worlds interpretation. So there is no conscious observer. So there's no consciousness as such.
Okay.
But if you're talking about consciousness as the drive which decides everything, then in both interpretations there is a consciousness. In the first interpretation, it is the observer itself that's the consciousness part, and in the other one, it is something that is driving the whole phenomena itself.
Okay.
Yes.
Yeah, in fact, the word existence, it means out there. It means out there. So, science, at least as far as I know, doesn't give as much weightage to consciousness as existence. So, I think that's probably the reason why we are not able to understand a few things or give because existence means actually what is out there. So, what is out there? What is it that is out there? That we say is consciousness.
Correct.
So, Pranav, one question. All these theories and interpretations is one sophisticated way of saying we cannot understand anything in the universe?
I want to put a more positive twist to it. So I'll say we are continuously trying to understand.
Okay.
So his job is never in doubt.
Eventually, if you look at things, Yes, eventually, if you, so that's why science exists, right? Because you are never done. There is infinite things to know.
Yeah.
We'll never go out of our jobs.
Yeah. Yeah, excellent.
Yeah, but
I
as
think
consciousness, you may not need the job at all.
And as consciousness, there is no science also.
Right.
Yeah.
The moment science brings consciousness, the end of science.
Yes.
That's why scientists don't want to look at consciousness also.
Yes, we'll lose our jobs.
excellent. Very good. So, any more questions from anybody else? I think, yeah, I think mostly we are done. So, thanks, Pranav. It's been really a wonderful talk and a lot of, food for thought and a lot of, thinking about this. And it's really exciting. Thanks a lot for your talk. Okay. Are you?
Just one question, Pranav. So
Yes.
about parallel universe is one thing. Past, present, and
Yeah.
future, they exist simultaneously also. That's also multiple universe.
So, so for now, you should give me definitions again. What do you mean by past, present, future, and how are you relating them to multiple universes?
So
So,
all the things which happen in the past, all things happen in the future, all things which happen in the present moment, all are there simultaneously available at this moment. Is it multiple universe?
right now, no.
No. Okay.
Yes.
Okay.
So, so you can consider each. So, I guess what you can do is you can consider each chunk in time. So, okay, physicists have a concept of what time is. Uh, we we have some very precise definitions of how time comes about through relativity and things. So based on that, we can have concepts of time, and there are theories that allow you to do time travel and all of these things. It's just that there are some conditions that have to be met according to the present theories that we have. For example, all theories that correspond to time travel requires you to break the speed of light. So breaking the speed of light right now is not a physical phenomena yet, so we don't know. If you're looking at quantum mechanics, you can say there because of these multiple superpositions, you can think of it as, all of these chunks of past, present, and future are readily available to you. You can think of it that way. But the thing is, the quantum mechanics that we understand as of now, time and space are still not like time is not quantum mechanical. So general theory of relativity doesn't have a quantum mechanical analog. There's no quantum general relativity yet. So all quantum mechanics is happening on a space-time continuum, which is not quantum mechanical. So everything is based on that space. So the space-time is still not quantum mechanical yet. We don't have a quantum theory over there yet. So
There's
if you
nothing
have a
called quantum space.
no. So if you have a quantum space, if you have quantum time, then these possibilities open up for sure.
Okay.
But we don't have an analog for that yet, because if you want an analog for that, again you'll have to like if you have quantum theories, then you can hop on between these things. But yeah, it's not there.
Okay. Thank you, Pranav.
Yeah.
Okay. Thanks, Pranav.
Thank you.
Thanks, everyone.